Okay, welcome to a new week. We have a lot of induction to do, but first we're just going to quickly go through as many of the midterm problems as we can. I don't really want to spend too much time on it. I will try to explain it very quickly, and maybe after the lecture is done at 11 or something, I can take any outstanding questions. Okay, so the tests are almost done being marked. I think we just probably need today and maybe half of tomorrow to finish marking them, and then I will, post the results and all that other good stuff. So here, let's just quickly take out some of these problems. So the first full solution question is a Gauss's law question. It's telling you here that there are charged disks, green disks, and that the pink shells are imaginary Gaussian surfaces. And what you are told in the problem is that you do know, somehow magically, that each Gaussian surface is experiencing the same magnitude of electric field. And the question is saying, does that mean there's the same flux that passes through each of the shells if, in fact, it's the same E field that passes through? So there's two ways to sort of do this. You know that flux is equal to E times A, and if you know E is constant, and you're told in the question, A is getting bigger. A is getting bigger, right? Each pink shell, each subsequent pink shell is larger than the previous one. So if E is constant and A is bigger, then you know the flux is getting bigger as well. So that's one way to think about it. The other way to think about it is you know that flux is proportional to the enclosed charge. And you're told that the disks have Q, 2Q, and 3Q of charge on each of the conducting shells, the green conducting shells. So another way to think about this is flux is proportional to total enclosed charge, which means if there's a Gaussian surface that is encompassing more total charge, then it will have more total flux. So either way, we'll get you the right answer on that one. The second full solution question. You have two positive charges. They could be two protons. They could just be two positive charges. It doesn't really matter. At locations A and B, the premise is there are three different ways in which you can move particle A to particle B, path 1, path 2, or path 3. Question 1 says, is sphere A being moved to a higher or lower potential? The answer here is higher potential. And the brief justification would be positive charges will spontaneously move to a lower potential. And if you were to allow this charge to naturally flow, there would be a repulsion force between these two. So it would spontaneously move away. So, moving toward would then be a higher potential. It's the opposite of that. And of course, answers may vary. You could say things like it's a Coulombic voltage, KQ over R is getting smaller, and stuff like that. So there's multiple correct answers, but any subset of those correct answers would be fine. Rank the three paths according to the required work. Well, work is going to be Q delta V. So this does not depend on path, whether we go a straight line, a curvy line, it doesn't matter. Delta V is just the voltage where you start compared to the voltage where you end. And that's the same in all three cases. So this is going to be the same. All three paths are going to be the same total required work. If you had version 2 is very similar. We're just using the same principles, but sort of just in a different wrapping of question. Here we have an insulating ball, and we're asking you to rank the E field in various locations. So again, flux is proportional to total enclosed charge. And it'll be Coulombic, so it'll be KQ over R squared. So that's the premise of it. We see here that A is inside of the charged insulating sphere. So most of the charge is still there for A to experience. So A will be the largest one. B is just outside the sphere, so B will be slightly next because it's slightly farther away. A isn't even farther away, actually. A is sort of like inside. Then C is where things get, there's a little bit of a wrinkle with C. C is inside of a neutral conductor, as the question describes. So C is actually inside of a Faraday cage, FC, a Faraday cage. So C is actually going to feel 0 electric field because it's inside of a Faraday cage. And then D, we've seen in lecture, there's almost a diagram almost exactly like this, that outside of a conducting shell, the E field will propagate as if the shell wasn't even there. So D will feel an E field as if it's a certain distance away. So your ranking there is A, B, D, and then C, where C is equal to 0. And the reason being, again, the justification would be Gauss's law, would be the justification there. I mean, you can't just write Gauss's law, you have to give a little bit more, you have to explain the Faraday cage and the distance, but those are details that, you know, even mentioning those words would probably get you most of the answer. This question here, we have charged semicircular or quarter circle pipes. So this one here is saying to rank the E field at the center, and B is rank the voltage at the center. So these are all a bunch of charged, positively charged particles, each of which is contributing a tiny E field vector at the center. And then we're asked to compare what that would be with respect to each other. So here, A is whatever A would be. B, we have things pointing down like this, but we also have things pointing on the other side. So there's a little bit of superposition there. So B is slightly larger than A. Now C, however, C has E fields pointing this way, but it also has E fields. Oh, it didn't change color. I don't know. Okay, it will not change color. Welcome to Microsoft products. Okay, well, this segment down here will work in reverse. So it turns out that these two segments will perfectly cancel out, and C is actually the same scenario as A in terms of electric field. And then D is even more hilarious because you have both diagonals canceling each other out. So D, it comes last, and it comes last specifically because there's no electric field, no net electric field at the center. And part B just really tests the students' knowledge to see if they understand the difference between a vector and a scalar, where the E field is a vector, the voltage is a scalar. So with B, you don't actually add vectors, meaning, you know, you can still have two positive contributions with the vectors, but if they're in opposite directions, they will cancel out. With voltage, that's not the case. They're just scalar. So voltage, the more positive charge you have surrounding the origin, the more voltage there is. So this is just simply D bigger than C, bigger than B, bigger than A. And here I would just say voltage is scalar. Okay, so that's that. Okay, moving right along. You know, here we have a plate that is charged, two charged plates, causing an E field and, you know, thus deflecting a charged object. And we are measuring a deflection angle of 30 degrees, and we want to know what the voltage is as a result of that. So this is an equilibrium question. I still can't change color. Interesting. Hold on, I'm just going to try minimizing, and will that work now? Aha, there we go. Now I can change color. So here we just have to draw a free body diagram. So we have tension coming up this way. We have gravity coming down, and then we have something obviously pushing it to the right. That's going to be the electric force. So there's your free body diagram. And then it's an equilibrium. So the next thing to do would be F net equals MA, which equals 0. This thing is not accelerating at all. And we have F net X, F net Y. So I don't know, maybe I just feel like doing F net in the Y direction first because, I don't know, why not? So that equals 0. The F net in the Y direction is going to be the tension in the Y direction and then gravity. So tension in the Y direction is equal to gravity. So this is going to be tension cos theta equals mg. And then F net in the X direction is going to equal also 0. In the x direction, what am I looking at? I'm looking at tension in the x direction, and I'm looking at the electric field, or the electric force. This is going to be tension sine theta equals Q times E, whatever the E field happens to be. And then you plug everything in, and let's eliminate tension, shall we? So plug tension into here, and we're going to get mg tan theta, and that's going to equal QE. So that's most of it. Then we ask ourselves, well, what kind of E field is this? Is this a Coulombic E field? Is this an E field due to, you know, a long infinite wire, whatever? This is an E field due to a parallel plate capacitor. So we ask ourselves, well, what's the E field of a parallel plate capacitor? We have two options for that. We've got Q over epsilon naught A, and we have delta V over D. So then we say, okay, well, they're both valid. Which one's more useful in this case? So we go back to the question. We know that we're given the distance between the plates, evidenced by the diagram here. And we're also asked for the potential difference between the plates, delta V. So we should be using delta V over D for E there. And then finally, you would get, if you rearranged everything, you would get delta V equals mg d over Q tan theta. So there is your final derived equation. I think if you plug everything in, I think you get about 48 volts. What is the charge density on the plates? Okay, so now you're asked something about how much charge is on the plates. So, you know, here we use the coupling of the two valid equations. So Q over epsilon naught A is going to equal delta V over D. We have delta V from the previous question. We have D stated in the question, 5 centimeters. However, we don't have the area of the plates, and we don't have the charge of the plates. However, they're not asking for charge, they're asking for charge density, Q over A. So simply, we can just rearrange for Q over A, and then you see here, let's call that sigma, Q over A, let's just call that sigma. You can call it whatever you want. If you want to call it rho, that's cool too. It honestly doesn't matter. And if you rearrange, you're going to get delta V over epsilon naught over D. So there you go. And I think if you plug all that in, I think you're going to get something like 8.46 nanocoulombs. Oops, not nano P, nanocoulombs. Okay. C, Mark found 32 AA batteries around my house. That's the mechanism by which I was able to charge these plates. Describe how I can use 32 individual batteries to provide a 48 volts, because each battery is only 1.5 volts. So, you know, if you found 32 batteries, new batteries laying around your house, how could you use them to generate a larger voltage? The answer here is you put them in series. Put the batteries in series. So if you put the batteries in series, you get, if each battery was 1.5 volts, then, you know, from our lessons with Kirchhoff's rules, you know, every time you pass over a battery in the loop, you know, depending what side you're traveling, you're either adding the voltage of the battery or subtracting the voltage of the battery. So when batteries are in series with one another, you know, you're climbing 1.5 volts, climbing 1.5 volts, climbing 1.5 volts. If you climb through 3 batteries, you're at 4.5 volts. So if you climb through 32 batteries, you're at 48 volts. And there was a bit of a hidden Easter egg there that, you know, 32 times 1.5 is 48, which is the answer to part A, it's 48 volts. D, how would the equilibrium angle change if the string were not exactly midway? So the question described that I was holding this charged object exactly halfway between these two plates. So this was testing students' knowledge to see if they understood the E field inside a parallel plate capacitor was constant. And it is constant. So even if I held the string here, it would produce the same angle, because it's not like the E field is any stronger or weaker closer to one of the two plates. So here it would be unchanged because constant E field. Okay. 3.2, there are many parallels between gravity and Coulombic forces, blah, 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 blah. Determine a formula for an electron speed if it were to be in a stable orbit around a helium nucleus of radius 2r. So they're asking about a formula, so we don't necessarily need to plug in any values. So if you had a helium nucleus, you have 2 protons in a helium nucleus, and then you have an electron sort of traveling in circular motion around it. So if we were to draw a free body diagram of this, the only force acting on this electron would be an attraction force, an electrical attraction force between a negative and a positive, so they attract each other. Just like the moon orbits around the Earth, the force of gravity is an attractive force. But despite this attractive force, the moon does not come crashing down to the Earth's surface because it's in a stable orbit. Presumably, the premise of this problem is, so is the electron. Despite this sort of force of attraction, it's in a stable orbit. So here, our free body diagram, FBD, is just one force. It's the electric force down. So we do what we learned in 136, free body diagram, then we go with F net equals ma. We are in circular motion here, so it's not just regular A, it is centripetal A. So we just write A sub C there. The net force, as I can see from my free body diagram, is just the electric force, and this is going to be mv squared over r. And the electric force, I ask myself, well, what kind of electric force is it? You know, is it due to a constant E field like in the parallel plates? No, this is going to be Coulombic. It's between 2 individually charged objects, one object being the electron, the other charged object being the nucleus. You know, there might be 2 neutrons in there as well, but neutrons are neutrons, they don't have a charge. So overall, the nucleus has a +2 charge. So this is going to be K Q of the electron times 2 times Q of the electron, because it's 2 protons. And the proton, nicely enough in nature, the proton has the same magnitude of charge, just opposite sign as the electron. So in terms of variables, we can just say it's 2 times that of an electron. Over r squared, and this equals mv squared over r. And all we do here is we simply cancel what we can. And what are they asking for? They're asking for the electron speed. So here we can rearrange for speed. So speed equals the square root of 2k qe squared over rm. There you go. So there is the formula for the electron speed. And for part B, we're borrowing another concept from 136, you know, energy. So describe or derive a formula for the escape velocity of the electron. Well, with planets and orbits and celestial orbits and satellites, it's the same idea. We know that if something is in a stable orbit in a satellite, like the moon, then if it were to decrease its tangential velocity a little bit, then what would happen is the radius of orbit would shrink a little bit because, you know, gravity would be pulling it in. But as it shrinks, as the moon starts to fall toward Earth, it would speed up, and it would speed up enough to regain a stable orbit. So if it loses some energy, it goes to fall, but as it falls, it speeds back up and it finds its stable orbit again. Similarly, if it gains some speed, maybe there's some thrusters on the satellite or the International Space Station or something, and you go to speed up, then the required force to keep it at that radius wouldn't be able to be there, because gravity, I mean, it's not like friction where you can have like up to a certain maximum. Gravity at a point is gravity at a point. So if it starts traveling too fast, mv squared over r goes up, so the radius will increase, and the radius will keep increasing until the force of gravity is such that you know, it can hold it in that orbit at that speed. So it's sort of like a buffer zone, right? You can have a wide range of stable orbits that are stable if you perturb the speed a little bit. However, there's a maximum to that. you know, if for a certain orbit, if you like quadruple the speed, it will continue increasing its radius of orbit, but it'll just float away because there's just the celestial object was given too much kinetic energy that gravity was not able to combat that. So there's inherently a sort of maximum to that as well. Think of it like chemistry when you have buffered solutions in an equilibrium. A buffered solution resists small changes to pH. But however, it's not perfect. I mean, if you really try hard to change the pH, if you just dump a bunch of baking soda in, you will absolutely make it more basic. So that's what's happening here. That's what escape velocity is at what speed do you need to give it in the moment to escape from the orbit without readjusting to a stable orbit. And this is done using a simple equation, a simple conservation of energy equation. So that's where you sort of equate potential energy to kinetic energy. So in this case, we have, kinetic energy being 1/2 mass of the electron, v of the electron squared. And it's not gravitational potential energy in this case. I should say it's potential energy. So potential energy in a celestial, like the moon case, would be gravitational potential energy. In our case, the potential energy is electric, not gravity. So this would be K QE times 2QE over R. So KQQ over R is the gravitational, the electrical potential energy. And then what we're doing here is we're just simply rearranging. We're simply rearranging for the escape velocity V. So we solve for V and we get 4K QE squared over RM. And part C asks you to compare your answers in A and B. Does this follow the same pattern that we see in a gravitational orbit? And the answer is yes. Yes, it does. The only real difference between the escape velocity and the stable orbital velocity is a factor of √2. So the difference between stable velocity and escape velocity is the square √2. And that pattern is noticed with gravity as well, when you're talking about orbits of celestial things like satellites and moons and planets and stuff like that, a stable orbit is always √2 smaller than its escape velocity. And last but not least, here is a sort of circuit question. And this, for those of you who have used assignment 2 to practice, this is verbatim from assignment 2. So this is a bit of a reward for students who used assignment 2 as practice for the test, even though it wasn't marked. So if it wasn't marked, understandably, students may not have attempted it or focused on it. Even though I was saying all the questions on it are very relevant for the midterm, I chose to reward students who listened to that advice and used assignment 2 for practice, because you should be rewarded for your hard work when possible. So here's that question. I think many of you, I haven't looked at the results of this question yet, but I think many of you hopefully got it because you would have seen it before. And that brings me back to something else I'll talk about momentarily. But here's the circuit. Part A says, what is the charge on each capacitor? So step 1 is realizing that you have the same voltage difference between, let's say, part A and part B. So, you have capacitor 1 has a certain voltage difference, and then you have capacitor 2 in series with capacitor 3, in series with capacitor 4, and it also experiences the same voltage difference as its counterpart C1 because they're in parallel with one another. So we want to know the charge on each capacitor. Well, the first one is the easiest, I would think, to figure out. So the first one is simply Q equals CV. And so this is going to be C1 V1. And V1 is just the voltage from the battery, which was, in the question, what was the voltage of the battery? 50 volts. And do we have C1 in the question? C1 was 10 picofarads. So 10 times 10 to the minus 12 times 50. So this is going to be 5 times 10 to the minus 10, oopsies, 10 coulombs. So that's the charge on the first one. And then the second one, you would have to find an equivalent capacitance, not an equivalent resistance. These are not resistors, they're capacitors. And capacitors in series, you find the reciprocals, so 1 over C1 plus 1 over C2 plus 1 over C3. And I think if you plug everything in, oh no, not C1, sorry, C2, C3, and C4. So if you plug everything in, you're going to get 1 over 20 plus 1 over 30 plus 1 over 40. And if you plug everything in, if my math is correct, I think you get 250 over 13 times 10 to the minus 12 farads. Now, if you used a calculator to get a decimal number, that's cool too. If you have me with 136, you know I absolutely hate calculators. So I don't trust them because I don't trust myself with a calculator. I always mess up the punching in of the numbers and something always goes wrong. So whenever possible, I try to make sure it's a fraction because then, you know, it's easier to double check your math that way. So once you have this, you can say conservation of charge. You know, when two capacitors are in series with one another, you know, these two plates, this positive plate and this negative plate, are touching each other. So they have to have the same and opposite charge as each other, which means each capacitor has to have the same amount of charge on it. So here we can say Q equals C equivalent times V. And we know that the V is between A and B. So it's the same 50 volts as it was before. So this is going to be 250 over 13 times 10 to the minus 12 times 50 equals Q. And if you go about doing that, I think you're going to end up getting, again, assuming my calculator skills are competent, I think you're going to end up getting 461.5 times 10 to the minus 12 coulombs. I think, assuming my calculator skills are correct. B asks for, oh, it's not scrolling. There we go. B is asking for the voltage across each capacitor. So B, come on, B is, well, we know the voltage across C1. The voltage across C1 is just the voltage of the battery. So the voltage across C1 is simply 50 volts. Okay. For the other ones, the voltage across C, oops, not CC, the voltage across C2 is going to be found with the equation Q equals CV. So we know the charge on each capacitor Q, right? The charge on each capacitor was 461.5 picocoulombs. So we know what that is. So we can solve for the voltage on Q2, and it's going to be the charge divided by C2, the capacitance 2. So if you plug that in, you're going to get something like 461 divided by, what's the C2? I think it's 20 picofarads times 10 to the minus 12 times 10 to the minus 12. And if you go through there, I think you're going to end up getting, for C2, I think that's something like 23 volts or something like that. And then you do the same for VC3, oops, right near the bottom of the screen, VC3, Q over C3, 461 divided by 30. And that's going to be, I think, 15.4 volts. And then VC4 is going to be Q over C4, 461 over 40. And I think that's going to be something like 11.5 volts. Okay. And there's the test, the full solution and full solution and short answer part of your test. So there you go. Okay. I will, like, if we've got time at the end of the lecture, I'll take up some questions at the end of the lecture, but we have a lot of induction to do. So I just wanted to make sure I took up the test in some fashion. So I will post this video separately, and then we're gonna mosey on over to induction very shortly. Okay, see you in the next video.